Have you ever paused to consider how your email makes its invisible journey from your computer to a friend's inbox, maybe halfway across the world?
Or how that streaming video just, well, magically appears on your screen,
Right.
perfectly synced, doesn't matter where it came from.
Yeah, it all just works, right? And honestly, we usually don't think twice about it.
We just expect it to.
Exactly. So today, we're taking a deep dive into this fascinating, really intricate world of computer networking,
Uh-huh.
specifically how networks actually move data from one device to another. It's like the invisible infrastructure that powers our entire digital lives.
And we've got some excellent source material lined up. Stuff that really peels back the layers, from what you actually see as a user
Right.
all the way down to the underlying blueprints that make it all possible.
Yeah, the goal here, our mission, is really to unpack the core concepts, and there are some surprising historical twists, too.
Oh, definitely.
And just the ingenious design that lets your phone talk to a server across the globe without you needing, like, an engineering degree.
What?
Think of it as your shortcut to really understanding that silent, tireless machinery behind your online world.
And we'll explore not just the how data moves, but also the why behind it, giving you context for maybe some networking terms you've heard tossed around,
Mm.
and highlighting some of the clever problem solving that went into it. You're going to gain some serious clarity, I think, on what makes the internet, well, the internet.
Okay, let's start with the everyday view, your perspective.
Mm-hmm.
When you connect at home, you probably use, what, DSL or cable? A high-speed connection?
Sure. Maybe an Ethernet cable plugged right into your PC,
Mhm.
or Wi-Fi for your tablet or phone.
And at work or school, it's pretty similar, isn't it? Ethernet into a wall jack or maybe Wi-Fi in the conference room?
It's actually quite remarkable how consistent those underlying networking technologies are. Whether you're at home, with a small office setup,
The say network, yeah.
or you're part of a huge enterprise system. The scale is different, obviously, but the fundamentals, they're strikingly similar.
And here's what's really interesting, I think. Many of us, and I definitely include myself here sometimes, we just enjoy the functions, right? Posting on social media, making video calls, searching for stuff,
Yeah, just using it.
without much thought about how our favorite device actually connects. It's a bit like driving a car without really understanding the engine.
That's a great analogy. It gets you where you need to go,
Right.
but you're missing all the elegant engineering under the hood.
Yeah, you don't need to know how the carburetor works to get groceries.
Exactly. But, knowing a little bit about what's under the hood can give you a whole new appreciation.
Sure.
Because really, no matter how much you already know, the core job of any network, whether it's powering your Netflix habit or, a global bank,
Yeah.
it boils down to one incredibly simple goal:
Yeah.
reliably moving data from one device to another. That's it.
Huh. Just moving data.
Everything we're about to discuss, all the complexity, it's all geared towards achieving that single fundamental task.
Okay, so if the job is just moving data, why does it seem so complex? And why do we need this formal thing called a networking model?
Well, a networking model, or you could call it a blueprint, it's essentially a comprehensive set of documents.
Okay.
And each document describes one small, specific function. But together, collectively, they define everything needed for a computer network to actually work.
Ah, okay. So it really is like an architectural blueprint for a house.
Exactly like that.
You could try building a house without a blueprint, I guess,
You could try.
but it might fall down, or the plumbing wouldn't connect to the right places.
Right. The blueprint makes sure you have the right foundation, the right structure, the hidden spaces for pipes and wires.
And importantly, that all the different workers, the framers, the electricians, the plumbers, can follow the same plan.
Without messing each other up, yeah.
So trying to build a network without a model would be, what, digital chaos?
Pretty much. An exercise in frustration for sure. It's so much easier and more reliable to just buy and use products that already conform to a well-known model.
Right, so things actually work together.
Precisely. It ensures products from different companies, different vendors can communicate seamlessly. It prevents that digital Tower of Babel situation.
That makes total sense. But you mentioned history earlier. It wasn't always this neat and tidy, was it? There was this battle of the networking models.
Oh, absolutely right. Go back to the 1970s, 1980s. The networking scene was incredibly fragmented, kind of chaotic.
How so?
Well, big vendors like IBM, they had their own proprietary models, like IBM's SNA, Systems Network Architecture from '74.
Okay.
So if your company bought computers from, say, 3 different vendors. You often needed 3 separate incompatible networks.
Wow. 3 networks just to connect different computers in the same company.
Yeah, and then you had to somehow figure out how to bridge them together. Imagine the complexity, the cost.
Yikes.
Uh,
Okay, so the world clearly needed something better. An open, vendor-neutral solution.
exactly. And 2 major contenders emerged from that need.
Which were?
First, there was the OSI model, Open Systems Interconnection. That came from the ISO, the International Organization for Standardization, a very formal body.
Okay, sounds official.
And second, there was TCP/IP, which actually originated from a U.S. Department of Defense contract, believe it or not, and was largely developed by, well, volunteers.
Volunteers versus a big international standards body. Interesting matchup.
Very. ISO had this really noble, ambitious goal: standardize all data networking protocols for all computers globally.
Sounds good on paper.
But their process, because it was so formal, was pretty slow.
Mm.
Lots of meticulous debate on every single detail.
Bureaucracy, maybe?
You could say that. Meanwhile, the less formal, volunteer-driven effort behind TCP/IP, it was just building momentum much, much faster. More practical, maybe?
And this is where the story gets really interesting, right? Because through the 90s, companies were kind of hedging their bets, using OSI or TCP/IP or sometimes both.
That's right. It was a period of overlap and, frankly, some confusion.
But by the end of the decade,
TCP/IP had just emphatically dominated. OSI, despite its grand vision, kind of faded away.
wow. So now, here we are in the 21st century, and TCP/IP, the thing built initially by volunteers for a DoD project.
Yeah.
It's the most prolific, most pervasive network model ever created. It literally runs the internet.
It really is an amazing story. But here's the irony.
What's that?
Despite TCP/IP completely winning that battle, you'll still often hear terms related to OSI.
Really? Why?
Well, you'll probably never actually work on a computer using the full OSI protocols anymore. But understanding OSI's terminology, it's surprisingly essential for grasping a lot of modern networking jargon.
Huh. So its ghost kind of lingers in the language we use.
Exactly. It's a legacy that really stuck around.
Okay, so TCP/IP won the great protocol wars. Let's get into how it actually works. You mentioned it has layers. What's that all about?
Yes, layers. It's a way to make sense of all the different functions involved. To make a complex system understandable, you break it down.
Makes sense.
So the model organizes all these functions into categories, and we call these categories layers. Each layer includes specific protocols and standards related to its job.
And the TCP/IP model we use today, how many layers does it have?
The common model we focus on has 5 core layers.
5. Okay, what are they?
Starting from the bottom, you've got the physical layer, then data link, then network, then transport, and finally at the top, the application layer.
Physical, data link, network, transport, application. Got it. And briefly, what does each one do?
Okay, quick tour. The physical layer is all about the actual transmission, sending the raw bits, the ones and zeros over a link, then cables, fiber optics, radio waves, the electrical signals themselves.
Okay, the real hardware level.
Right. Then the data link layer handles sending data reliably over one specific type of physical link, like sending data across an Ethernet cable or over a single Wi-Fi connection.
Just one hop.
Exactly. Then the network layer takes a broader view. Its job is delivering data across the entire path, from the original sender all the way to the final destination, no matter how many different networks or hops it crosses. This is where routing happens.
Ah, okay. The big picture delivery.
Yep. And the top 2 layers, transport and application, they're more focused on the software, the applications that actually need to send and receive that data. They provide services directly to the programs you use.
Let's start at the top then with the application layer, because that feels like where we as users live most of the time.
That makes sense.
So what's happening at this layer when you say, open your web browser and go to a website?
Okay, so the application layer provides services to your software, like your browser. It doesn't define the browser itself, but it defines the communication services that browser needs.
Like what?
Like HTTP, Hypertext Transfer Protocol.
Sure.
HTTP defines how your web browser requests web pages and how the web server sends them back.
So if our source uses the example of Bob wanting to see Larry's web page, what's happening with HTTP there?
Bob's browser uses HTTP to send a message to Larry's web server. The message basically says, hey, give me your web page, specifying the file, maybe home.htm.
Okay.
Larry's server then uses HTTP to send back the contents of that home.htm file. It's this back and forth defined by HTTP that lets you browse the web.
And it's kind of amazing to think Tim Berners-Lee created HTTP back in the early 90s specifically for this purpose, right? To make the World Wide Web possible.
Absolutely. It was fundamental.
And that HTTP you see at the start of a web address, that literally means that HTTP is the protocol being used for that conversation.
That's exactly what it signifies, yes.
Now, you mentioned messages. When Bob asks for the page, he sends this message. Does it have extra info?
It does. He sends an HTTP header. Think of headers like an envelope for the message.
Okay.
It contains information. The HTTP protocol needs to work, like what Bob is requesting, what browser he's using, stuff like that.
And when Larry's server responds?
It also sends an HTTP header with the page data. And importantly, this response header contains a return code.
A return code? Like what?
Well, if everything's okay, it's usually 200, which just means, okay, here's the page.
But what if it's not okay? Like the page isn't there?
Then you get a different code. If you've ever seen that HTTP 404 not found error,
Oh yeah, definitely seen that one.
that's a return code. The server is using HTTP to tell your browser, sorry, couldn't find that specific file.
Huh. So those error codes are part of the protocol.
They are. And HTTP is also designed to be efficient. If Larry's page is large, it might be sent in multiple chunks or messages.
Right.
But instead of wastefully repeating the whole header on every single chunk, subsequent messages might just send the data, making the transfer faster.
Okay, so the application layer, like HTTP, handles the request and the response. But what if something goes wrong during the trip?
Good question.
What if Bob's request gets lost? Or maybe one of those chunks of Larry's web page vanishes somewhere in the digital ether. The page wouldn't load properly.
That brings up a really critical point.
Yeah.
How do we guarantee delivery? Especially when the underlying network can sometimes be, well, unreliable. Things get dropped.
Yeah. So how?
That's precisely where the next layer down, the transport layer, comes in. And specifically, the most famous protocol there, TCP, the Transmission Control Protocol.
TCP, part of TCP/IP.
The very same. TCP provides an absolutely crucial service to the application layer, like HTTP. And that service is error recovery, making things reliable.
Okay, reliability. How does TCP actually do that? What's the mechanism?
It primarily uses acknowledgments.
Yeah.
It's quite clever, actually.
How does it work?
Okay, imagine Larry's server needs to send, say, 3 chunks of the web page to Bob's browser using TCP.
All right.
TCP, on Larry's side, gives each chunk a unique sequence number. Let's say 1, 2, and 3.
Okay, numbered chunks.
Now imagine chunk number 2 gets lost somewhere in the network. It just disappears.
Happens.
Bob TCP receives chunk 1 and chunk 3. It listens to sequence numbers and immediately realizes, hey, wait a minute, number 2 is missing.
It notices the gap.
Exactly. So Bob's TCP sends a message back to Larry's TCP. This message is an acknowledgement, but it basically says, I got 1 and 3, but I need you to resend number 2.
And Larry's TCP then resends just that missing piece.
Precisely. It resends chunk 2, Bob's TCP receives it, puts it in the right order with 1 and 3, and then hands the complete correct data up to the browser.
Wow, that's remarkably clever. It's like a built-in checking system. It guarantees eventually everything gets where it needs to go, even if the network drops things.
That's the core idea of TCP's reliability, yes.
And this really highlights 2 important concepts you mentioned earlier.
Yeah.
First, adjacent layer interaction. HTTP, up in the application layer, needs reliability.
Right. It needs error recovery.
But it doesn't do it itself. It relies on TCP, the layer right below it, to provide that service. They cooperate.
Perfectly put. The higher layer uses the services of the layer below it.
And the second concept, same layer interaction.
Yeah.
Larry's TCP is setting those sequence numbers and sending the chunks. Bob's TCP is receiving them, checking the numbers, and sending acknowledgments back.
They are communicating with each other using the rules of the TCP protocol. Even though the actual data has to travel down the layers on Larry's side and up the layers on Bob's side,
Right.
logically, Larry's TCP is talking directly to Bob's TCP, that same layer interaction.
Okay, so application layer requests stuff, transport layer, like TCP, ensures it gets there reliably between the 2 computers.
Correct.
But how does that data navigate the huge, complex internet, going from Larry's network, maybe through several other networks, to eventually reach Bob's network?
Now we're moving down another layer to the network layer. And this is where the Internet Protocol, or IP, lives.
The other half of TCP/IP.
Exactly. The name TCP/IP comes from these 2 protocols being so fundamental and commonly used together, TCP at the transport layer, IP at the network layer.
So what's IP's main job?
Its job is addressing and routing, getting the data packet from the original source network all the way to the final destination network across potentially many intermediate networks.
Okay, addressing and routing. Our source material uses a great analogy here, right? The postal service.
Yes, it's a fantastic way to understand IP.
So imagine you write two letters. One's going to a friend just across town, the other to someone across the country.
Okay.
You put the addresses on them, add stamps, and drop both into the same mailbox.
Right. As the sender, you don't need to know the specific route each letter will take. You just address it and send it.
But the postal service, they do need to know the route.
Absolutely.
Yeah.
They look at the address on each letter and decide where to send it next. The local letter might just go on a local truck, the cross-country letter. It might go to a sorting facility, get put on a plane, maybe go through another sorting facility, then onto another truck.
It makes multiple hops with decisions made at each point.
Precisely. Each post office or sorting center looks at the destination address and makes a decision about the next step in the journey.
Okay, so how does this map to networking and IP?
Well, your application and transport layers like HTTP and TCP, they act like you, the person writing and sending the letter.
Oh, so?
They prepare the data, the message, and then they just hand it off to the network layer, to IP, and basically say, deliver this.
Yeah.
They don't care if the destination's on the same local network or halfway around the world.
They just trust the layer below to handle the delivery logistics.
Exactly. And it's the lower layers, particularly IP in the network layer, that act like that postal service for your digital messages.
Okay, so IP is the postal service. What are the key parts it defines?
Two main things. First, IP defines that every computer connected to the network needs a unique IP address.
Like a unique postal address for every house.
Precisely. It's a globally unique identifier for that device on the network.
And the second thing?
IP defines the process of routing. This involves specialized devices called routers.
Routers. I've heard of those, like my home Wi-Fi router.
Similar concept, yes, though internet core routers are much more powerful. These routers work exactly like those post offices or sorting centers in the analogy.
They make forwarding decisions.
Correct. They receive an incoming data packet, look at the destination IP address in the packet's header.
Ah, IP adds its own header, too.
Oh, yes. The IP header contains the source and destination IP addresses, among other things. Crucial information.
Okay. So the router looks at the destination IP address,
Compares it to its internal routing table, its list of known networks and directions, and makes a decision about which connection, which road, to send the packet out on next to get it closer to its final destination.
So let's use the example again. Larry, maybe his IP is 1.1, wants to send data to Bob at 2.2.2.2.
Right.
Larry's computer, using its IP process, sends the packet, which now has an IP header, to a nearby router, let's call it R1.
Right. Larry's computer doesn't need to know the whole path, just the address of its local post office, R1. It trusts R1 to handle it from there.
So R1 gets the packet. What does it do?
R1 looks at the destination IP address, 2.2.2.2. It consults its routing table. Maybe its table says, to reach network starting with 2, send packets out interface X towards router R2.
So it forwards the packet to R2.
Exactly. R2 then receives the packet, looks at the destination 2.2.2.2 again, checks its routing table, and maybe forwards it directly to Bob's local network, or perhaps to another router, R3.
And this continues, hop by hop, router by router.
Until the packet finally arrives at a router connected to Bob's local network, which then delivers it to Bob's computer, 2.2.2.2.
Wow, this whole forwarding process, that's IP routing.
That is IP routing in a nutshell. It's truly the core mechanism that allows data to move across the diverse, interconnected networks that make up the global internet.
Okay, this is making sense. Application asks for data, transport, TCP, make sure it's reliable end-to-end. Network IP routes it globally using addresses.
You've got the top 3 layers down.
But we still haven't talked about how the data physically moves between, say, Larry's computer and router R1, or between R1 and R2. How does a packet actually become, like, electrical signals on a wire?
Now we're diving down to the bottom 2 layers, the data link and physical layers.
Okay. What's their job?
Their combined job is to define all the protocols and, importantly, the hardware needed to deliver data over a specific type of physical connection. One single link or hop.
So focusing on just one step of the journey.
Exactly. The physical layer, layer 1, deals with the absolute basics, the cabling, like Ethernet copper wires, fiber optic cables, the connectors, and the energy used to transmit the bits, electrical voltages, pulses of light, radio waves.
The actual physics of transmission.
Right. And the data link layer, layer 2, defines the rules and protocols for using that physical media correctly to send data between 2 devices directly connected on that link.
Like Ethernet or Wi-Fi protocols.
Precisely. Ethernet is a classic example of data link and physical layer standards working together for wired networks. Wi-Fi, or IE 802.1, does the same for wireless LANs.
Okay, let's walk through that example again. Larry's sending an IP packet just to the first router, R1, over his local Ethernet LAN. What happens at these bottom two layers?
Great example. There are basically 4 key steps for this single hop.
Okay, step one.
Step 1, encapsulation. Larry's computer takes the IP packet, which already has the IP header and the TCP header and the application data inside.
The whole layered thing.
Yes, and it wraps it in another envelope specific to Ethernet this time. It adds an Ethernet header and, unique to this layer, an Ethernet trailer. This whole thing, header, IP packet, trailer, is now called an Ethernet frame.
So it gets wrapped again for local delivery. What's in the Ethernet header trailer?
The header contains things like their image addresses, the hardware addresses of Larry's network card and router R1's network card on that specific LAN segment. The trailer often contains error-checking information for that frame.
Okay, so now we have an Ethernet frame. Step two.
Step 2, transmission. Larry's network card, operating at the physical layer, takes the bits of this Ethernet frame and actually transmits them as electrical signals over the Ethernet cable connecting to R1.
It becomes electricity.
Or light pulses if it's fiber, yes. Step 3, reception. Reader R1's Ethernet port, also at the physical layer, receives those electrical signals and meticulously recreates the original sequence of bits that made up the frame.
Okay, signals back to bits. And step 4.
Step 4, decapsulation. R1's data link layer process looks at the incoming frame. It checks destination MAC address. Yep, it's for me. Maybe verifies the error check in the trailer. Then, crucially, it strips off and discards the Ethernet header and trailer.
It unwraps the Ethernet envelope.
Exactly, and what's left inside? The original IP packet. R1 now has the IP packet ready to be processed by its network layer, which means looking at the destination IP address and deciding where to route it next.
Wow. So that whole process, wrap it in a frame, send signals, receive signals, unwrap the frame, happens just for that one hop from Larry to R1.
Yes, and it happens again for the next hop, say from R1 to R2, though maybe over a different type of link, like fiber optic. R1 would take the IP packet, encapsulate it in a new frame suitable for that fiber link, transmit it, R2 would receive it, de-encapsulate it.
So this framing and unframing happens at every single hop along the path.
That's exactly right. It's how IP packets can travel across all sorts of different physical network technologies seamlessly. The data link layer handles the specifics of each individual link.
That really ties it all together. This process of adding headers and sometimes trailers at each layer as the data goes down, it sounds like putting on layers of clothes or like a digital onion.
It absolutely is. And the technical term for this wrapping process is encapsulation.
Encapsulation.
Yeah. When your computer prepares data to be sent, each layer adds its own control information, usually a header, and sometimes a trailer at the data link layer to the data it received from the layer just above it.
So it gets progressively wrapped up as it goes down the stack.
Precisely. It's like adding a new layer to that onion. Application data get an application header, then that gets wrapped in a transport header like TCP, then that gets wrapped in a network header, IP, then that gets wrapped in a data link header and trailer like Ethernet, and finally, the physical layer sends the bits.
Okay, let's recap that sending process, maybe as a 5-step summary mirroring the layers.
Good idea.
Step 1. The application creates its data and adds any necessary application layer header.
Okay.
Step 2. The transport layer takes that, adds its header, maybe TCP for reliability, or sometimes UDP for speed, creating a segment.
Right, a TCP segment or UDP datagram.
Step 3. The network layer takes the segment, adds its IP header with the source and destination IP addresses, creating an IP packet.
The packet, yes.
Step 4. The data link layer takes the IP packet, adds its header, like Ethernet with MS addresses, and its trailer, creating a frame.
Frame for the local link.
Step 5. Finally, the physical layer takes the frame and transmits it as a sequence of bits, electrical signals, light pulses, radio waves.
That's the complete encapsulation process, top to bottom. And of course, the receiving computer does the reverse. De-encapsulation, layer by layer.
Understanding this encapsulation really helps clarify some of the jargon, doesn't it? You hear people talk about segments, packets, and frames.
Exactly. They aren't just random synonyms for message. They refer to the message at a specific layer, defined by the outermost header it's currently wearing.
So a segment is specifically the message at the transport layer with a TCP or UDP header.
Generally, yes, though sometimes you hear datagram for UDP, but segment is common for TCP.
A packet is the message at the network layer, identified by having an IP header.
Correct. The unit that gets routed across the internet is the IP packet.
And a frame is the message down at the data link layer with the link-specific header and trailer, like an Ethernet frame.
You got it. segment, packet, frame. Each corresponds to a different layer and a different stage of the journey.
Now, here's that crucial point again about the old OSI model terms. You said even though TCP/IP won, we still hear things like Layer 7 protocol or Layer 3 PDU.
Right. It still crops up all the time.
Why? Why didn't we just switch completely to saying application layer protocol or network layer packet?
It really comes down to history and habit. The OSI model, with its 7 layers, was heavily discussed and taught during a formative period, maybe the late 80s, early 90s.
Okay.
And a lot of its terminology just became ingrained in how network engineers and IT professionals talked and wrote.
Even after TCP/IP took over.
Especially because the functions of the bottom 4 layers of the 5-layer TCP/IP model we discussed, transport, network, data link, physical map, very closely to layers 4, 3, 2, and 1 of the 7-layer OSI model. They even have the exact same names.
So transport is layer 4 in both, network is layer 3, data link is layer 2, physical is layer 1.
Precisely. So when someone says layer 3, everyone knows they mean the network layer, the layer where IP operates. It became a convenient shorthand.
And layer 7, since TCP/IP only has 5 layers.
Layer 7 in OSI corresponds to the application layer in TCP/IP. So when people talk about a layer 7 firewall or layer 7 protocol, they're generally referring to things happening at the application layer of the TCP/IP stack, like filtering based on HTTP traffic.
Got it. And that term PDU, protocol data unit?
That's a generic OSI term. It just means the message at any given layer. So an IP packet is technically the layer 3 PDU, an Ethernet frame is a layer 2 PDU, a TCP segment is the layer 4 PDU.
So it's just a general way to refer to the message unit at whatever layer you're discussing.
Exactly. It's still useful sometimes when you want to talk generally without specifying segment, packet, or frame. It's all part of that lingering OSI vocabulary.
Wow. Okay. We started this just thinking about clicking a link or sending an email.
Yeah, the simple stuff we do every day.
And now we've peeled back all these layers. We've seen how application requests become transport segments, then network packets, then data link frames, then finally just electrical signals or light pulses.
And how TCP adds reliability, how IP routes things globally using addresses, how Ethernet handles the local delivery.
It's an incredible, intricate journey for every single bit of data.
And what's truly remarkable is that all of this complex dance, happens seamlessly, usually in fractions of a second, every single time you interact with the network.
Yeah.
And the foundation of our entire digital world really rests on these incredibly well-defined layered blueprints. These protocols that allow completely different systems built by different people all over the world to work together reliably.
Built largely by volunteers, no less, in the case of TCP/IP's origins.
Quite amazing when you think about it.
So maybe the next time your webpage just pops up instantly, or that video call connects without a hitch, you'll have a bit more appreciation for that intricate, unseen ballet of protocols, headers, encapsulation, and layers happening just beneath the surface.
This deep dive, I hope, has really shown the ingenuity behind it all. A layered system that, through persistence and collaboration, ultimately connected the entire world.
So, here's something to think about the next time you go online. What part of this incredible behind-the-scenes network machinery stands out most to you? What piece of this complex puzzle do you find most fascinating now that you've seen under the hood?